Hi everyone, how are you doing? Just let me know if audio, video, everything is fine. So today we are going to, do a marathon on cache memory, as all of you knows. So let's just see this topic entirely. Before that, you can just confirm if everything is fine, if audio, video, everything is fine from your end also. Okay, so just let me know. Okay, okay. So I think we can just start, right? So this topic, cache memory, that we are going to start today is basically one of the most demanding topic or one of the most asked topic I can say in entire gate computer science among all the topics gate computer science. So let's just see this topic very nicely. We will solve many gate PYQs today, and other than gate PYQs also we will solve many other questions. Okay. So just to give you the numbers, there have been approximately, okay, not approximately. I mean the number which I'm going to write here, it is only lower bound. So there can be more than that, but yeah, there has been, you can say, 70 plus questions. Okay, asked in past 40 years just from the cache memory. Okay, there have been 70 plus questions. So let me just adjust my video so that you can see the screen properly. So there have been 70 plus questions, as I'm saying here, have been asked in the last you can say 40 years or 45 years. Okay. So generally there is a trend that no, I can say the trend is that from last 15 years is that they ask around two questions. Okay, from last 15 years I can say, from last 15 years or 10 to 15 years I can say, they ask two questions every year. So this single topic can give you 3 to 4 marks. Okay, every year. This is the power of this single topic. Okay, so this single topic itself is very powerful. Okay. So, so some of you are asking that are there any prerequisites? No, there is no prerequisites. You can directly attend this. Okay, so there is no prerequisites. You can say you can directly attend this session. Okay. So one of the person is asking, are there any prerequisites? So let me just tell you, there is nothing. Okay, so let's just get started. So answer of this question is no. Okay, so let me quickly read out the chats. Okay, some of the person is saying that sir, will you start in this particular session? Will be doing write back and write through questions. So let me just tell you that there has been only 1-2 questions that have been asked from write back and write through. So I will not be focusing on write back write through because it is a very rarely asked topic. Okay, so as you can see here that only 1 or 2 questions have been asked from write back or write through. Most of the question, every time they ask questions from these topics, so we will be just focusing very particularly in this particular session we will be focusing on these two. In fact, last year also from this and this only they have asked. Okay, last to last year also I think from this and this only. So they have been asking, many questions they have been asking from these two particular areas. From write back or write through policies. Okay, from these write policies they are not asking. Yes, we should study it, and we will be taking, probably we will be taking one session to complete this. Okay, there has been already one video on the website, but over the YouTube also we might be taking it. Now, before I go further, let me quickly tell you that AIMTs are already announced. So this is the again just to let you know that we are having AIMT one on 22nd of the December, which means just on Sunday. So AIMT one has already been announced, and we will be having this on the Sunday. Okay, so at 2:30 p.m. The most interesting part is that it is free for all. Okay, so all AMTs, not just this, all AMTs are free for all. Okay, So if you want to know more information about the AMT, we have already taken a live session. Just search this keyword, okay, or we will be putting the link in the description for this particular video, or you can see that there has been this session just 9 days ago, okay. So you can see this particular session as we have already taken this session, okay. Okay, so now let's just get started with our agenda, which is cache memory. So by the way, at 2:30 p.m. we will be having the first AMT, 9:30 a.m. and 2:30 p.m. These are the dates, 22nd of December, and then 28th, and then 5th of January. Okay. So how to attempt? You will be getting a button on the Go Classes homepage. So here you will be getting a button to attempt AMT. Okay, attempt AMT. Something like this you will be getting here. Now let's just start with the cache memory. So in the gate, there has been, questions related to cache memory, particularly tag words, index words, etc. There has been questions related to loops and arrays. There has been questions related to time, for example, L1 cache time, L2 cache time, something like that. And these particularly, this is, I can say, in the decreasing order. This is most asked and then most asked. So almost, they ask two questions. I can say every year, almost these two topics are only covered. So this topic, generally 2-mark question. This topic generally 1-mark question. Okay, but yes, sometimes they also ask from the effective access time also. Okay, from this particular area. Sometimes they also ask from this particular area. Write back, write through policy, they never ask. I mean, 1-2 questions are there, not more than that. Okay. Yeah, so let's just start with this cache memory. What are the prerequisites? There is no prerequisites. You can directly watch this video, I mean, without any fear or without anything in your mind. Okay, so now let's just get started. Okay. Yes. In this session will also be available as a recorded format, so don't worry about it. Okay. So see, as most of you might be knowing about the CPU, so this is CPU and this is your memory, and both are connected with the memory bus. Even if you don't know, that's fine. Even this is your first topic of your computer organization, that is perfectly fine. I'm just asking, if you know, that's fine. If you don't know, that's also fine. Okay. So both are connected with a memory bus, but the problem here is that this memory is big. Okay, this memory is big and the access time of the memory is slow because of the design. I mean, from the capacitors and all this has been made up. Because of that, this main memory is slow. Okay, so you can say that this main memory is slow. So that is why we have the cache. Okay, so let me just give you an analogy here, that main memory is bigger but faster, just like some truck. Okay, and this cache memory is smaller but faster. Okay, so main memory is bigger but slower, just like some truck, but cache memory is smaller, just like your small car. Okay, your family car, or maybe some sports car. Okay, you can say it is a sports car, right? It is smaller but faster. Now in between the main memory and the CPU, we can put cache so that our work can be speed up. Okay, that is the main agenda of the cache memory, right? But why does this work? I mean, what is the benefit of putting some smaller memory in between? Let's just see this quickly. Okay, why caching works? For example, there is a concept called locality. Okay, because of this locality, this caching generally works. What does this mean? Let me just tell you. Suppose you are accessing the similar element. See, generally we do that only, right? Suppose I'm writing int I equal to 0. I mean, in the for loop, if I'm writing int I equal to 0, something like this, right? And then I do I plus plus always. So I'm again and again referring I. So it many times happens that we refer to some particular location in the memory again and again, right? So this is the reason I can say that this caching works. Why? What we can do? We can take this element and then we can put this element instead of main memory. We can put this element into cache. This is called temporal locality. There is something called a special locality, which means if we are accessing this element, then probably we will be accessing the nearby element in the future. So for example, if this is our memory, okay, if this is our memory, then if let's suppose some element is stored here, Generally, let's suppose, let me take the example of array. Let's suppose this is some array element which is A0 is stored here, then A1 will be stored here, right? And A2 will be stored here. Generally, let's suppose we are working with the array. So it is rarely happens that if I'm accessing this and then I'm accessing A30 or something like that. For example, if I'm doing some sum, then I will be doing something like this, right? If I'm doing some sum in the array, in the loop, okay, something like this, right? If I'm doing some sum in the loop, then I will be doing something like this: sum equal to sum plus ai, which means first I will be accessing a0, then a1, then a2, which means nearby elements. The tendency is that we access the nearby elements. I can say, if I've already accessed a0, then we are going to access a1. That is the more chance, right? Okay. So if you have already accessed A1, then probably you are going to access A2. So that's called a spatial locality. Temporal locality means if I'm accessing some element again and again. A spatial locality means if I have accessed this element, then probably I will be accessing the next element in the next access. So let's just do a quick example. Suppose this is some for loop that I have written. In this for loop, I'm summing up some array. If I just ask you that which of the following follow the temporal locality in this code, temporal locality means I'm accessing the same thing again and again. Am I accessing I again and again? Yes. Am I accessing sum again and again? Yes. Am I accessing elements of the array? No, right? I mean, again and again, I'm not accessing only A0. So A0 got access only one time, right? And then A1 got access, then A2 got access. So basically, if I talk about the temporal locality, then yes, I is following temporal locality, sum is following temporal locality, but is elements of array following temporal locality? No. A0 is not getting access again and again, right? Not getting accessed again and again. Do you all agree with me? So that is why I will say that these two elements follow the temporal locality. What about the spatial locality, right? Do I follow spatial locality, which means wherever I is stored in the memory. See, memory is generally your kind of 1D array, which means this is first byte, then second byte, then third byte, then fourth byte, right? So suppose I is stored here, okay, at some location. Maybe this location is 1000. Then are you going to access 1001 for sure in the next iteration? I mean, is this a chance that you are going to access 1001 in this using this particular loop? No, right? Some might have been stored, let's suppose, at some location. Maybe it is 2000, right? Some is stored at 2000 location. Are you going to access 2001 next? No. So that is why I is not following the spatial locality. Some is not following the spatial locality. Spatial locality means if you have accessed some element, then are you going to access the next in the next iteration? Are you going to access the subsequent element or the adjacent element, right? So if you have access, let's suppose, some element of array which is A0, are you going to access this A1? Yes. Are you going to access this A2? Yes. So you are accessing the nearby elements, right? So that's why elements of array are following the spatial locality. Okay. Is this understood to everyone? Now let's just move further. Okay. I hope this is understood to everyone, as most of you have given the correct answer. Okay. Most of you have given the correct answer. So for example, let me just even tell that who have given the correct answer for this question. So these people have already given the correct answer. This, yes, element of the array, or array element, like this, right? Okay. So now let's just move to the next thing. So you have your memory, right? And then I said, like, you have your cache. So we have just seen that, okay, cache works. I mean, there is, some kind of intuition or some kind of proof that we have done that, okay, having a cache makes sense. Okay, this is your memory, this is your cache. But let's just do one thing. That, see, what we want to do, we want to put some of the data from the memory to the cache, right? So let's just do one thing to better organize this. What we can do, we can divide this memory and we can divide this cache into number of parts. For example, I divide this memory also into some number of chunks. I divide this cache also. Okay, I'm dividing memory and cache both. So is this fine to everyone? That we have memory, we have cache. Now what we want to do? We want to divide memory and we want to divide cache. So what I have done, I have divided this memory and cache something like this, right? Something like this. Okay. So I hope that is fine to all of you guys. Now this particular thing is called, uh, see this in the chunk that we are dividing the memory, this particular thing is called block, okay, or line, and this particular thing is called line. So basically I divide memory into blocks, I divide cache into lines, right? Now interestingly, I divide in such a way that block size and line size is same. Okay, so I'm dividing the memory, I'm dividing the cache, but I'm dividing in such a way that block size and line size is same. Okay, so which means if I'm dividing, let's suppose from here to here, if I'm dividing this into let's suppose 4 bytes each. Okay, 4 bytes each. Can you tell me what is the division here? What is the size of the line? If the block size is 4 bytes, what is the size of the line? Line size will also be 4 bytes. Okay, there won't be any difference in that. Understood? Okay, great. I hope this is understood to everyone. Now, now what we want to do, our aim is that we want to pick some of the data here. Now we are refining ourselves to say that, okay, we will pick one of the block, okay, or one of the line. You can interchangeably use, there is no harm in this because the size is same, right? So we will be taking one of the block and we will be putting this one of the block in one of the line, right? So we want to shift some of the data from memory to cache. Now we will be picking one of the block to shift in one of the line, and it will exactly fit, right? I mean, there is no extra space or less space. So one of the block will get exactly fitted into one of the line. Now which line you should be putting into? Okay, this is the bigger question. See, we want to well organize everything. Okay, I don't want to randomly put out something. We want to have some way. We want to have some mechanism. We want to have some way by which I can put this into one of the line. Okay, so I hope my question is clear. What I want to say is that that where to put the data in the cache, right? Where to put the data in the cache. For example, if this is the data or this is the one of the block. This is one of the block. Okay, these are the block ID or block numbers. So if this is one of the block, then where to put this block in the cache? Okay. So this is the question, where to put this block in the cache? Is this question clear to everyone? See, once this question is clear, then only we will be, able to answer this question. And this question answer means a lot, because once we answer this question, then only we will be able to understand the things very clearly. Okay. So what to do, right? I mean, how to put any block in the line? So this is a bigger question. So there are 3 ways to do it. One is called direct mapped. Okay, another one is called set associative. Another one is called fully associative. There are 3 ways to map one of the block into the line. Okay, so is question clear? See, now we are starting the cache memory topic. So what we are saying, that we have the data in the memory, we have the data and we want to transfer the data in the cache. Some of the data we want to transfer. For that, what was the first step? We have divided the memory into we have divided the memory into the blocks, right? So we have divided the memory into the blocks. Let me just put the frame here. Okay, now once we have divided the memory into the blocks, then we have also divided the cache memory into the lines, such that the line size and the block size is same. This is done, right? Now what we want to do, we want to shift some of the blocks from memory to the cache memory, from main memory to the cache. Okay, we want to shift some of the blocks. Now let's suppose I want to shift block number 9. Okay, suppose there are 0 to 15. How many blocks are there? If I say 0 to 15, then how many blocks will you say? It will be 16 blocks, right? It will be 16 blocks. So now suppose I want to shift block number, as you can see here, block number 9. Then in which cache line it will go? Okay, so this is the question that I want to answer. And that has been answered using 3 ways. By the way, what do you think? That this 9 should go to 0, 1, 2, 3? I mean, there has to be some fixed mapping. Okay, which means later on if someone asks me, there has to be some formula or something, right? Because if later on someone asks me, then I should be able to tell it immediately that okay, this 9 should be here. something like that, right? Okay, I'm just giving you some intuition that you should be having some formal ways. So these are the three ways which will answer the only one question, that given this main memory, all of these three ways which will answer just one question, that given this main memory, given this cache, okay, so the main memory and cache are given to you, let's suppose. Now there is some block here, and these are obviously lines here. Now this block will go to which line? Okay, which line? Either we will answer this. I mean, you can either implement direct map, you can or implement set associative, or you can implement fully associative. So we will be answering this either using direct map, set associative, or fully associative. Okay, so let's just see this. Now again, the question remains same, that where to place this block in the cache. Okay, so let's just see that how to answer this question. Now direct map cache says that suppose you want to shift this, right? It says that you will be using mod formula, which means let's suppose this is block number 0, block number 1, block number 2, block number 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so suppose this is block number 12. I mean, numbering is starting from 0. Okay, if it is block number 12, now this is block number 12. Now direct map says that you map this 12 to, if these are the number of lines are how much in this cache, number of lines are 8. Okay, number of lines are 8. So direct map says that you do one thing, you just do the mod operation. So 12 mod 8 is what? If you do the mod operation, 12 mod 8, it will be 4. So you map it to 4. Okay, similarly, there is something that set associative says, there is something that fully associative says. Fully associative in fact says that you can map to anywhere. Okay, I mean, there is no problem, you can map to any of the block, you can store this into any of the block. That's what fully associative says. Set associative says that you should map it to, okay, see, it is saying you should always map to 4, direct map. Set associative says you can map it to either this or this. It gives a choice, it gives a set. Okay, so direct map says you directly map to only one of this. If this is full, then you can replace it. I mean, if it is having already some other data, you can replace this. Okay, depending on your choice. This is what direct map says. You should directly map to only one. Set says that you should map it to some set. Okay, I mean, either you put here or here. It is your choice. Fully associative says that you can put this anywhere. Now you might be thinking that okay, fully associative is better, or something like that too. Or maybe you might be thinking that direct map is better. Okay, so you may be saying that okay, fully associative is better. Why? Because you have flexibility here, right? You can put anywhere. But problem will be that we need to check that okay, where it is present. I mean, the search time will be more. We will see this later on. But yeah, you can little bit guess that if I'm putting it anywhere, then obviously I have to search whenever I need this block. I have to search. Okay, it is here, 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 or here, right? Then search time will be more, right? Here it is lesser search time. Here it is lesser search time, and here it is little more. But I think it is better. So maybe depending on your thought, depending on your implementation, you might be using direct map, set associative, or fully associative. But we will see all of this in very good detail. Okay, is this little bit definition in very little bit form, is this clear that what is direct map? It is saying you just map to one of them. Set associative, you have multiple choice. Fully associative, you can map to any one of them. Okay, let's see this in very good detail, in more details. Okay, okay, so now let's just continue. Let's just start the very first topic, which is direct map cache. Okay, there has been many gate PYQs on direct map cache. Okay, we will solve all of them. I mean, most of them we will be solving. Okay, at least I can say most of the tricky questions we will be solving, right? So there has been many gate PYQs. Okay, so as it is saying, direct map cache, it is the simplest approach. It says that each memory belongs to exactly one cache block. Okay, so if you want to map this X, it will be going only to here. Okay, I mean, it is like either it will be going here if you want, otherwise you will not be shifting. I mean, if you don't want to replace this particular block, if it is already containing some data, probably you don't want to replace for some reason, then it will not, it will reside in the main memory. Okay, I mean, if you want to keep it, you have to keep it here only. There is only direct mapping. Okay, that's why the name says it is direct map, because we are mapping directly. Now, now that's very interesting question. Okay, that's very interesting question that you might like to answer. Suppose, see, one thing is clear, that we are studying what, direct map, which means this particular one of the block will be mapping to the fixed line number. For example, if you give me, let's suppose 9, then 9 will map to only 1. Okay, if you give me 13, 13 will map to only 1, something like this. Okay, so this mapping is fixed. I mean, I will give you the mathematical formula how this mapping has been done, but let's just see this geometrically, or let's just see this with the figure. Suppose you have two choices. Okay, one of the approach is saying, that you are basically you are mapping in such a way that block number 0 is mapping to line number 1. I mean, 0 5 9, not 0, 1 5 9 and 13. 1 5 9 and 13 are mapping to line number 1. This is your one of the choice. Okay, suppose this is one of the choice, right? Now the second choice could be that you are mapping first 4 here in the first line. Okay, and the next 4 in the next line, and the next 4 in the next line, and the next 4 in the next line. So what do I mean by that? That you are mapping, this block will go to here only, this block will also go to here only, this block will also go to here only, this block will also go to here only. So let's suppose there is some array. Okay, let's suppose one of the line is containing, I mean, I'm not going to merge of the detail, but let's suppose one of the line is containing only 2 element. Okay, a0 a1 a2 a3, something like this, a4 a5 a6 a7. Suppose these are the 8 elements of the array. Okay, here also the same elements, right? Here also the same elements, on the left side also there are same elements. Maybe I can just copy paste. Okay, something like this. I mean, here also same elements, here also same elements, right? So I can even write it, a0 a1 a2 a3 a4 a5 a6 a7. Now suppose these are the two approaches. One approach says that you map this to just one. Then is this approach better? Is the left approach better or the right approach better? Can you tell me? Is the left approach better or the right approach better? Left is better. Why? Let me just tell you why. See, what is happening here, that you are mapping, right? You are mapping this. Let's suppose you are mapping this block to this line. Now suppose you are accessing the array element, you will access a0. Generally we access then a1, then we access a2, then we access a3. I mean, we will access a0 a1, right? So if you are accessing a0, then you will put the whole block. See, we will be, let's suppose, putting the whole block in this line. Then a0 a1 is present. The next time, once you want to access a2, you have to actually do what? You have to actually say that, okay, let me just cross validate it, or let me just replace this. Okay, so you have to replace this with a2 and a3, right? Are you getting my point? So if you are mapping, see, if you are mapping this contiguous blocks to just one of the line, okay, and then continuous blocks to one of the line, then the problem here is that you have to basically replace again and again, right? a0 a1, and then at a2 you have to replace, at a4 you have to replace, at a6 you have to replace. But here this will map to this particular sorry, this 0 will map to 0. Okay, 1 will map to, I will tell you later on, 1 will map to this particular will map to this, and this particular will map to this. Okay, so see, if you are having this kind of choices, then at a0 you will be basically accessing this, and then at a2 you will not be you do not have to replace, right? And it's not about the replacement, okay? It's actually about the multiple access. If you are accessing this A0 again, then you can again access from the cache. But here, if you're accessing A0 again, since the A0 got replaced, that is the problem. Okay, you're losing your locality. So basically, if you're having this access again and if you want to access this array again and again, right, then you are not utilizing cache much. But here you once you shift the whole array in the cache, see the cache can hold the whole array, right? A2 and then and so on, right? Cache can hold the whole array. So once this cache have the whole array, you will be having the more flexibility, or you can say you are utilizing the locality, right? You are making more use of the cache. So if the choices are given, then you will be preferring this one. Okay. Anyway, this is not much required to solve the questions. It is just to build the intuition. Okay. It is just to build the intuition that in the left side, your cache will be holding the whole array at once, holding whole array at once, right? In the right side, the cache will just be holding one of only two elements, right? At once. At one time, cache will only be holding. Cache can only hold two elements of array at one time. Now, what is the benefit? Can anyone tell me what is the benefit of holding all the array elements in the cache? Because if I want to do multiple access, okay, that's important. If I want to do multiple access, then it is better in the case one, and that's what we do generally, right? So what we will be doing, we will be mapping like this, okay, which means we will be mapping, let's suppose 1, 1, 5, 9 and 13 to this particular one, or maybe I can say let me just tell you how we will be mapping. You know what we will be doing. If I want to map, then I will be mapping this to, let's suppose this is 0, 1, 2, 3, 4, 5, 6. I will be mapping this to 0. I will be mapping this to 1. I will be mapping this to 2, then 3, then 4, then 5, then 6. Okay. Then again, I will be mapping this to 0, then 1, then 2, then 3, then 4, then 5, and then 6. Like this, and then 0, and so on. Okay. So basically, I will be mapping in this way, 0 to 6, then alternate 0 to 6. Okay. See, that is what we have discussed. Other choice could have been you map this to 0, this to also 0, this to also 0, this to, I mean, first 6 maybe, or 6 or 7, whatever. It is just a hypothetical example, but I'm just telling you. Okay. 1, 2, 3, 4, 5, 6, 4, 5, 6, 7. Okay. So first 7 you can map to, 0, and then this to 1, and then this to 2. It won't be much useful. Why? Because if you are mapping this to 0, this to also 0, then once you access this, then you have to replace, right? Little bit you might be understanding, otherwise that's okay. I'm just assuming it is a bit of revision, but even if you are if you are watching this very first time, it's okay. Okay, because we will be covering everything in very good detail just now. So basically, our idea is that we will be basically having this particular way, right? Now, what is this particular way is called? This is basically modulo operation, which means let me just tell you. See, I want to map this to 0, this to 1. These are the 0 to 3, right? This to 2, this to 3, and then again I want to map this to 0, this to 1, this to 2, this to 3. Then again I want to map this to 0, this to 1, this to 2, this to 3. Then again I want to map, let's suppose this to 0, this to 1, this to 2, this to 3, right? In that case, as you can see, the block numbers, right? The block number is 0, 1, 2, 3, 4, 5, 6, 7. It will be keep on increasing. If you divide this, or if you take the modulus with these are the 4 lines, okay? If you take the modulus 4, then if you take the modulo 4 here, it will be 0, giving you 0. Modulo 4 will be giving you 1. Modulo 4 will be giving you 2. Modulo 4 will be giving you 3. Then again modulo 4 will be giving you 0. Again modulo 4 will be giving you 1. Again modulo 4 will be giving you 2. Again modulo 4 will be giving you 3. Again modulo 4 will be giving you 0. So that's very beautiful design, right? So see, if I want to map like this, 0, 1, 2, 3, then 0, 1, 2, 3, then 0, 1, 2, 3, then 0, 1, 2, 3. If I want to map like this, then the best thing that I can do is the modulo operation. Do you all agree with me or not? If I want to map like this, then I will be taking what? I will be taking the block number. So if someone asks me, what is the line number in which I will be mapping? Then what is your answer? Tell me. What is the line number in which I will be mapping? If someone asks me this kind of question, then I will say it is. Let me go to the next page. If I just ask you, let's suppose, what is the block number, or what is the line number in which you will be mapping? Line number means cache line, okay? You will be mapping will be block number, whatever is the block number, modulo, let's suppose in this case it is 4, I mean number of lines. It is basically 4 is number of lines. Okay, this is the summary, or this is the crux of the direct mapped. Okay, this is called direct mapped. Okay, this is the formula that we have developed of direct map. I mean, we are not remembering the formula. Okay, I'm telling you that what is the intuition behind this formula. That what is our idea? We want to map like this. Okay, 0 1 2 3 0 1 2 3 0 1 2 3. It is possible using the modulo operation. Okay. See, many of the students just directly remember that, okay, we just need to remember that direct map means modulo operation. Okay, which is fine. Even if you remember, I'm not saying this is something wrong or right. Okay, what I'm saying here, I'm just telling you the intuition that we want to map 0 1 2 3 0 1 2 3 0 1 2 3. Why we want this conjugative? We want to be in the different places. If it is conjugative, I want it to be different places. Okay, I want this to be different, this to be different, this to be different, this to be different. If it is conjugative, I want it to be different places, because generally I access the conjugative only, so that it can whole be shifted to the cache. I don't want this to fight for each other. I don't want the neighbors to fight for each other. Okay, this is very important concept. That's called locality. I don't want these neighboring blocks to fight for each other. Understood? Okay. So basically the line number and the cache number has this relation. Cache block, or you can say cache line, is having main memory block mod number of cache lines. Okay. Let's just move to the next slide. Okay. So main memory address is also called as physical address. This physical address we divide into 3 parts. I will let you know what does this mean. One is called block offset, another one is called line number, another one is called tag. Okay, this is very important slide, but I will come to this in the questions. Okay, I mean, when I solve the questions, I will be just coming back to this again. Okay, so I think we can start with the questions. So let's just solve 1-2 questions which are standard questions from some standard universities, and then we will be going to the gate PYQs also. So what they are saying, that main memory is 2 power 16 bytes, which means main memory is 16 bits. I mean, there are 16 bits in the physical address. Okay, this is size is 16 bits. And the block size is 8 bytes. In the main memory or the physical address, what we will be doing, we will be dividing into 3 parts. One is called block offset. Okay, this is based on the block size. Another one is called index, or the line number. Another one is called tag. Okay, so what you will be doing, if the block size is 8 bytes, you will say that this is 2 power 3, right? 8 means 2 power 3. So block offset will be 3 bits, right? If block size is 8 bytes, then you can just represent in 2 power, and then that 3 will be your block offset. Okay, so 3 bits will be taking by your block offset. And then what they are again saying, assume the direct map cache consists of 32 lines. So number of lines are giving to you as 32, which means 2 power 5, right? 32 means 2 power 5. Since you write the line number here, so you will be writing 5. Okay, so 5 bits will be taken by the line number. How is a 16-bit memory, which is okay, 16-bit is already there, divided into tag, line, and byte number. So what is the tag? This is 5 plus 3, 8, and 8 is remaining. So 853 should be your answer. Okay. Okay, tag will be clear. Tag will be clear in just just in few slides. I have a different slide for the tag. Okay, tag will be clear in just few slides, right? So yes, so I think you Vicky is saying great answer. I think he is talking about this particular explanation, right? This particular explanation, that why we are doing the modular operation. Okay. So let's just do more questions and then you will probably understand it more. What they are saying, you are given a direct map cache of total of 256 bytes with a cache block size of 16 bytes. Okay. So they are saying 256 bytes is your cache size. Okay. So cache size you will be dividing. So let me just tell you. See, physical address you will be dividing into three parts. What are those three parts? One is called block offset. Okay. Block offset. Another one is called line number. We also call it index to be consistent with other mapping techniques, which are set associative and fully associative. But yeah, you can call it line number. Another one is called tag. Okay. Now cache size you will be dividing into two parts. What are those two parts? Line offset or the block offset, and then this will be just line number. Okay. So we will see that what does this mean. You are given a direct map cache of total of 256 bytes with a cache block size of 16 bytes. Okay. So how many lines will be there? See, the cache size is 2 power 256. It is 2 power 8 bytes, right? Cache block size. So block size is 2 power 4 bytes. So can you tell me number of lines or number of blocks? Number of lines. Let me write line because I'm talking about the cache. Okay. So what are the number of lines? It is 2 power 8 divided by 2 power 4, which will be 2 power 4 lines, right? Now, how many bits will you require for the cache block offset? Block offset will require 4 bits, right? If the physical address is 22 bits, if the total is 22 bits, so from here 4 is taken for this. Number of lines are 4. 4 is taken for number of lines. This is 8. How many bits are required for the tag? The first one is tag or the last one is tag. So how many bits? 22 minus 8, which is 14, right? So 14, 4, 4. So 14 and then 4 and then 4 is the correct answer. I mean, this is the address split. Okay, this is the address split. So Vicky's answer, Vicky is asking, sir, main memory divide by cache memory, then find tax bits or not? Yes, you can do that also. Okay, you can do that also, but I will come to that in the few other questions. So you don't need to apply that kind of formula here, but yes, you can do. Okay, okay. So now let's just continue. Now let's just solve this question. What they are saying: consider a machine with byte addressable main memory. Okay, 2 power 16 bytes are there, which means 16-bit main memory is there. So I think this is the byte address or the main memory address of some byte. Block size 8 bytes. So if this is main memory address of some byte, this is main memory address of some byte. Can you tell me in this particular question? Can you tell me what is the block offset? 2 power 3, right? Block offset is, I mean, this is 2 power 3, 3 bits. So you can say that 3 bits are taken for the block offset. So generally it is not useful. I mean, these bits are not useful. So you can say that, okay, I mean, that is only useful if we actually want to access the data. But yeah, just to get the line number of these things, these bits are generally not useful. But yeah, this is the block offset. Okay, this is the block offset. Assume that a direct map cache consisting of 32 lines is used with this machine. Since the line are 32, which is 2 power 5, so next 1, 2, 3, 4, 5. So these 5s will be used for the line number. Okay, these 5s will be used for the line number, right? Here are the addresses for some byte. What are the corresponding line numbers where each of these bytes will be stored? Okay, so they are asking the corresponding line numbers for each of these bytes will be stored. So which means what is the line number where it will be stored? What is the line number for this byte where this will be stored? You can tell with these 5 bits. Okay, so this is I think 3, right? So with line number 3 it will be stored. Okay, so in line number 3 it will be stored. This is 6, right? So in line number 6 it will be stored. Okay, so in line number 3 this byte will be stored. In line number 6 this byte will be stored. In line number 3 again this byte will be stored. In line number, what is this? Can anyone tell me quickly? 2 power 0, 2 power 1, 2 power 2, right? And then 2 power 3, 2 power 4. 16, sorry, 0, 1, 2, 3, 4. Yeah, so this is 16 plus 4, 20 plus 1, 21, right? Okay, 3, 6, 3, 21. Is this understood to everyone? Okay, great. Yes, so many people have given the correct answer, right? So let me just copy that answer. Okay, sorry. So anyway, I was just copy pasting, but that's fine. Okay, now let's just move to the next question, right? Now let's just move to the next question. So consider a direct map. This is a nice question. Okay. By the way, this kind of question has been asked in GATE 2024 or 23. I think 24 itself, right? In the last year itself, they have asked. Okay. The similar question. Similar question, I can say, in GATE 2024. Similar in the sense they have given the data in the decimal format. That's very interesting. Let's just see this question. Okay. So what they're saying, that direct map cache with 64 blocks. Okay. So number of blocks are given to you as 64 or number of lines are given to you as 64. So you can say number of lines 64. A block size or maybe line size, whatever, because they're talking about the cache, a 16 byte. To what line number? 1200 map. So they are saying, see, this is very interesting question. They are saying some byte address 1200 is there, right? This will map to which line number? Okay, so let me just tell you what they are trying to say. Suppose this is the main memory, right? Suppose this is the main memory. In this main memory, there are like many bytes stored. Okay, starting from byte number 0. So there may be byte number 0, which is, let's suppose, stored here. There may be byte number 1, which is, let's suppose, stored here. I mean, byte number 0 will be having some particular address, maybe 0000000 like this, right? Depending on how many bytes of address I have. But yeah, there is a byte number 0, there is a byte number 1. Similarly, there is a byte number 2, there is a byte number 3, like this, right? Similarly, there is byte number 1200. Okay, somewhere here byte number 1200 is there. Okay, this is the byte number 1200 or the byte address 1200. Okay, I mean, address is 1200, so probably this is 1201 or something like this, right? But it doesn't matter. Okay, so you tell me, if your block size is 16 bytes, which means 0 to 15 bytes. Okay, 0 to 15 bytes, 0 to 15 bytes in the block number 0. 16 to 31. Okay, see, you are adding 15 here, right? Then you are ending. So 16 to 31 in block 1, right? Because your block size is how much? 16 bytes, right? Your block size is 16 bytes. So 0 to 16 is in 0 to 15 is block 0, then 16 to 31 in block 1, and so on, right? Can you tell me what is the block number for this? This block number 0, block number is 0. It's I mean, if you want to get the block number, I think what you can do, you can just divide, okay, this byte number. If byte number is 16, then this is the block size, then okay, you will be getting 1. So 1 is the block number. So if you want to get the block number, let's suppose I want to get the block number of 32. What is the block number of 32? 32 divided by 16. 2 you are getting, right? I mean the integer part is 2. Then 2 is the block number. So you can say that 32 is stored at block number 2. This will be the block 2. Okay. Where is 33 stored? 33 will be also stored 2 point something. Then it is also stored at 2. Right? 33 is also stored at 2. So where is this 1200 stored? Can you tell me where is this 1200 stored? If you do this 1200 divided by 16, you will be getting exactly 75. Even if you get 75 point something, doesn't matter. Okay. So 75 is the block number. Okay. So this is the block number 75 where it is stored. First of all, is this clear to everyone or not? Okay. This should be very much clear to everyone. Right. So 75 is the block number where this 1200 byte is present. Now they are asking in which line it is present. They are not asking in which block it is present. See, our first step is to know that in which block it is there. Now this block to line mapping I know. How? This is just a formula of mod. Block to line mapping I know, right? See, they just increase little bit here. They are just increasing one step, which is this. Okay, just this division step. Would you imagine that this exact same question, or I can say, I mean exact in the sense that concept is exactly same, they've asked in this last year gate, and last year or 2023, I'm sorry if I'm not 100% sure, I think last year only. Okay, but at last year 2023, I'm little bit confused now. Okay, but yeah, that's fine. So but what I'm trying to say, that they just ask the question in the decimal. That's the only issue, not the issue, but they are just asking the question from very first principle. Okay, so now from block, what is the blocks, what is the number of lines? 64. So you just take the mod. Okay, so basically the first step is to know the block number. Let me write. Okay, step 1, block number is equal to 1200 divided by what is the block size? 16, right? 16. It will be 75. Now what is the step 2? Step 2 is easy. Given the block number, okay, block number to line number mapping, it is given by the standard formula. What is that standard formula? 75 mod what are the number of lines? 64. 75 mod 64. What it will come? Can you tell me quickly? 75 mod 64 will come 11, right? So you can see 11 is the correct answer. Okay, this is the correct answer. I mean, this is the line number where it will present. Okay, now this particular whole block will be shifted to line number 11. Okay, let me know if that is fine to everyone. Let me know if that is fine to everyone. Is this fine? Okay, now let's just do the same question. Let's just do the same question with the help of binary. Okay, with the help of binary. See what they are saying. 1200 is your byte address, right? 1200 is your address. Okay, probably if you write the binary of 1200, then this will come something like this. Okay, so this is the binary of 1200. They are asking the line number, right? Line number means, first tell me what is the block size, 16 bytes, right? Which means this is the block offset. Okay, so this will be your block offset. Now from here we need to take the what is the number of lines? Number of lines are 64. Okay, 64 means 6 bytes, 6 bits, 2 power 6, right? Okay, this is your line number. Okay, Is this correct? Okay. Can you tell me what is this? What is the line number that you will be getting? Or there is some mistake? Is the binary correct? Let me quickly check. Okay, what is 1200 in binary? Can anyone give me with the help of either ChatGPT or with the help of Google quickly? Okay, so 10. Let me just copy paste it. Can you just divide in the group of 4? Okay, I think binary was wrong. I'm sorry about it. That's why this whole mess up has happened. Okay, but I hope you understood the point. These are the 4. These are the next 4, right? So anyway, like if you just split, I think binary was wrong. So if you just split, I actually took the binary from ChatGPT, but somehow it gave me the wrong answer. Okay, so if you just split this, okay, I think this is also someone gave me the wrong binary again, but the correct one should be something like this. Okay, great. If you just let me just quickly tell you, if you just split this, then these are your block offset. This is your line number, right? This is your line number. Now the same question has been asked in GATE 2023 or 24. So they have given in the decimal and people were confused that what to do, right? So from here also you can say that 11 is the answer, right? From here you can say yes, 11 is the answer. Okay, 8 plus 3. This is 8 plus 3. So 11 is the answer. So if you convert that to decimal. So from here also you can say that 11 is the answer. From decimal also you can say 11 is the answer, right? So whichever is preferred. But I will ask you to know this also. Okay, although you can solve using the binary, but I will suggest you to know this also, because this is very important. Because if you don't know from the first principle, then it might trouble you for some other question. Okay, first know that, okay, from the first principle, that what we are doing, first know the block number and where it is stored, and then know the line number that it will map to. Okay, now as I'm saying that this will go to 0, this will go to 1, this will go to 2, this will go to 3, right? And then 0, then again 1, 2, 3, then this is 0, this is 1, something like this, right? Then 2, 3, this is 0, this is 1, something like this. So this will go to 1, this will also go to 1, this will also go to 1, and so on, right? This will also go to 1. So these will go to 1. Now since multiple blocks are going to just 1, right? I mean, if I need, I can put this here also. If that is needed, I will replace the existing one, I will put this. If I will replace the existing one, I will put this, and so on, right? If multiple things are mapping to just 1, then how to determine that which block is currently in the slot 1? Okay, in this particular line or this particular slot, which block is currently there, right? Okay, so someone is saying that can you sum up the first method? The first method is very easy. See, you have some address, right? You have some address. The address could be anything. Okay, you have some byte address. First, what you need to do, you need to know that where this byte is present. Okay, this address could be anything. Let's suppose this address is A. Okay, you need to know where this particular byte. Okay, this is the address of the byte. This is the address of the exact byte. Okay, this is only one byte stored here. Okay, so address of any byte. See, byte, addresses are only for bytes. Okay, address of byte, which means even if you say that, okay, this is the address of the array. Address of the array means the address of the first byte of the array. Okay, and then from there I will check that, okay, I need we always have the starting address only. Okay, CPU only generate the starting address. From there I will just check I need the 4 bytes from down the line, or I just need 1 byte, or and so on. Okay, so this is the address of the byte. Let's suppose this address, okay, this should be byte number 0, byte number 2, byte number 3, like this. Let's suppose this is byte number A. Okay, now you first need to check where it is present, in which block it is there, right? So let's suppose the block size, okay, block size is BS. Okay, or let's suppose it is 8 2 power 3. Okay, so you first do A divided by 2 power 3. Okay, this will give you the block number, right? Then from this block number, A divided by 2 power 3, this is your block number. Then you just need to do the mod with number of lines, right? Mod with number of lines. This will give you the line number. Okay, this will give you the line number. Is this little bit okay or not? Okay, in the binary, how do we map it? See, the complete address is A. Okay, this complete address is A. This is written as 0101, something like this. The whole thing is A. Okay, so if you divide with something, if you divide with, let's suppose, 2 power 3, division means we always talk about the first half. Okay, which means you neglect these 3 whenever you're dividing. Then this is A divided by 2 power 3. Okay, this is A divided by 2 power 3. Then whenever you do divide, it is basically means you are talking about the first half. Whenever you're doing the mod, it means you're talking about the second half. So basically now from here, if you are doing this mod, which means you are talking about this part. Okay, you are talking about the second half. You only have this a 2 power 3. Okay, if you are interested, then only you just see this, otherwise that's fine. You only have this a 2 power 3. Now from this a 2 power 3, we need the second half. Then this is why the mod a 2 power 3 mod number of lines. Okay, for the first half we need the division, for the second half we need the modulo operation. Okay, first half will give you the quotient, or what we say, this is the remainder, and I forgot, I think this is a quotient, right? So first half will give you this modulus will give you the, if you're doing the mod operation, it will always give you the remainder only. Okay, so if I'm mapping multiple blocks into just one of the line, and in that case the question naturally arises that particularly at this point in time it is holding 1 or holding 5 or holding 9 or holding 13, something like this, right? Which one it is holding? This is the natural question. So how to answer this question, which one it is holding? What we can do, we can basically have some tag, or have some some bits I can just store that, okay, currently it is holding block number 1. Okay, currently it is holding either block number 1 or block number, I can directly store the block number, right? But it is little too much. I will be storing the block number but not the entire block number. There is something called as tag bits I can store. For example, see here, one thing you might observe, if 1 is getting mapped, these are the block numbers, right? Then this last 01 is common. Last 01 is common, isn't it? See, earlier I was writing in the decimal. Maybe I can just copy that there also. Okay, these are the decimals, right? These are the decimals, or maybe I can just write like this. Okay, so see, these are the decimals, and I'm mapping 5, I'm mapping 5, I'm mapping 1, I'm mapping 9, and I'm mapping 13. I'm mapping these 4 into just 1. Now if you notice, there's this 01 is common, right? The last 01 is common in all of this. So I want to store the block number here in the binary. If you look at the binary, either I will be storing 0001, or I will be storing 0101, or I will be storing 1001, or I will be storing 1101, right? I mean, either I will be storing this one, I will say this is the block number, this is the complete block number. Okay, I will say that, okay, either the block number 1 is present, or the block number 5 is present, or the block number 9 is present, or the block number 13 is present. I can completely store the whole block number here. But if you observe that this 01 is common, so I will not store this 01. Okay, I will store the block number, but very smartly I will store, because I know if it is 1, then I can infer from this 1, I can infer this 01 anywhere will be there. Okay, something like that. Since it is common, right, so I will not be storing, I will just storing the differentiating factor. So what is the differentiating factor? Only I will be storing these 2 bits, okay, which is called tag bits. So from this block number, I will be storing some most significant parts only. Okay, so let me just tell you what do I mean by that. Okay, with the example, maybe it will be more clear. Okay, see, I will be storing tag number, but since this 01 is common in all of this, whichever is coming to 1, okay, this 01 is common, that is why I will not be storing 01. See, don't worry about that, why this is only 01. I mean, if it is 1, then it has to be actually 01, because this represents the line number. Okay, so you will be just getting to understand this in just few with this just few examples. Okay, so let's just see the example directly. Let's suppose this is the tag. Okay, I mean, let's suppose tag is just 2 bits. Okay, this is the tag that I'm currently storing. This is the data. Okay, now I want to know this data is from which block. Okay, W is from which block? Okay, that's what I want to know. I mean, the block line number 0 is currently holding which block? How will I get? See, if it is line number 0, then just assume that there will be, since there are 4 lines, so it will be just 0 0. Okay, so basically 01 is the tag, and then 0 0 you can append. Okay, so it is actually coming from this particular block. So this is the block number. What is this? This is 2 power 0, 2 power 1, 2 power 2, which means this is 4. Okay, currently I am holding 4. I mean, this particular line is holding block number 4. So basically 0 can hold either 0, I mean block number 0, block number 4, block number 8, block number 12, block number 16, and so on. Okay, I mean, main memory size could be anything, and then plus 4 will be there. So then 20, then 24, something like this, right? So it can hold either 0, 4, 8, 12, 16, like this, right? But since tag is just 2 bits, so probably this will be storing. So it can hold either 0, 4, 8, or 12. Okay, so which one it is currently holding? It will be given by the tag. If tag is 01, this is the tag, I will be appending 00 here, and I will get to know that what it is currently holding. Okay, so for example, what it is currently holding, since it is first, so 1 is anyway the tag, 01 I will be appending. So it is currently holding what is the binary of this? This is 2 power 0, 2 power 1, 2 power 2, 2 power 3. 8 plus 4. This is 8 plus 4, 12, and then 1, 13, right? Is this okay to everyone? So currently I am holding 13. I mean, it can actually hold 1. It can hold just like this. See, it can hold 0, 4, 8, 12. It can hold 1, 5, 9, and 13. Okay. So currently I am holding 13. Is this a little bit clear? Okay. Why we are appending 01? Because I'm currently at first line. Okay. Basically this I'm not storing this. See here I'm not storing this 01, right? I'm not storing this 01. I'm saying whenever I'm here, I will append it by default. Okay, so this is my convention. If I'm at 1, I will append 01. Since these are the 4, so 0 0, 0 1, 1 0, and 1 1. Okay, so these are the numberings, right? These are the line numbers. So I will anyway append the line number to get the block number. Okay, so these are the line numbers. So 0 0, 0 1, 1 0, and 1 1. So what is happening here? Let me just tell you with the picture. See, this is your physical memory. Okay, generally what we do, we divide this into 2 parts only. This is block offset. This is the whole thing block number, I'm interested in getting the block number, right? I'm interested in getting the block number. But if the cache is given, okay, I mean, you can divide into two parts, block number and block offset. But if cache is given, then the same thing, you're again dividing. Okay, your block number is again divided into two parts. I mean, this division is good, but now you're again dividing into two parts. Is cache is with respect to cache. If you're dealing with the cache memory, okay, which is called line number. Here you have the line number. These are the tag bits. Okay. Now, given the tag bits, if someone asks you, tell me the block number, the whole thing, what you will do? You will append the line number. Okay. See, given this tag bits, let's suppose this is 01. Someone ask you, give me the whole thing, which is a block number actually. Okay. If someone asks you, give me the whole thing, what will you do? You will anyway append the line number. Or won't you? Will you append or not? Okay. So Akshat is asking that why we are appending. See, my answer to this question is this. Just try to understand. Okay. Try to understand from here that you have the block number and block offset. Okay. But with respect to cache, whenever you're dealing with the cache, you are again dividing the block number into two parts, line number and the tag bits. If someone gives you this and asks you the whole block number, you will anyway append the line number. Right? Is this little bit okay to every one of you or not? Okay, so let me just go to the next slides. Probably you will get to understand more. Okay, just tell me if you have to solve this question. Okay, what is the answer? What is the block number if the tag is holding this? I hope this is visible. I'm actually trying to write more things in the same slide. That is why. Okay, is this visible? Let me know. So what they are saying, that what is the block number? They are just asking the block number. Okay, what is the block number it is currently holding? If tag number is 00, line number is, since this is 000110, right? Line number is 10. Can you tell me the block number? In the binary only you tell me. Quickly in the binary you tell me the block number. The block number is 0010, right? 0010 is your block number. Isn't it? Which is actually 2. Right? Great. Now let's just move to the next slide. Okay. So now here you tell me what is the block number. Okay. If someone give you the tag is 01, this is 01. Okay. Line number is 0001 10 and 11. Line number is 11. What is the block number? Block number you can take immediately say 0111, which is actually 7. Right? Okay. Is this understood to everyone or not? That how we are calculating the block number using the tag. See, whenever we are in the tag, yes, in the tag it is okay even if you store. Like if you want, you can store the whole block number, right? But it's not necessary. It's not necessary to store the whole block number. We are storing few bits only, because line number anyway we will be appending. Okay. If we want, we can store the whole thing and we can say that okay, we can avoid appending the line number. We can say the whole thing we can store as a tag. Yes, but it's not useful. Okay, because I can anyway infer from the line number. Okay. So this whole thing is the block number, which is tag number and the line number together. Understood? Okay. And cache, see. So this is your, you can say this is your physical memory. That's how you divide your physical memory, right? Now, similarly, you divide your cache memory into two parts. What are those two parts? Cache memory into two parts, which are line number and line offset or the block offset. You can say line number and block offset. You divide the cache memory because you just have, whatever is the line size, you will be saying, okay, this is a line number, and then this the, if you want, you can divide actually in the two parts, block offset or the lines offset, which means if the cache memory is, let's suppose, 2 power 8 bytes, right? And the cache, the block size is, let's suppose, 2 power 2 bytes. Then how many number of lines will be there? So you can say, okay, 2 power 2 bytes, it means this is 2, this is 8. So number of lines or line number will be containing 6. So number of lines will be 2 power 6. Okay. So from here you can say number of lines is 2 power 6. Okay. Now you observe here is that you are dividing your physical memory like this, right? Tag, line number, block offset, you can divide if you want your cache memory like this. Okay, line number, and because you just have line size and the cache memory, cache is whole, and then you can divide with the line size and then number of lines you will be getting from here, right? Then you can see that, okay, these things are common, right? Which means actually these are the, let's suppose, 3 bits, right? Then that's very interesting relationship. If these are the three bits, then you can say your physical memory or main memory size is basically 2 power 3 into your cache memory size. Okay, which means if tag is 3 bits, then what does this mean? See, you can understand this intuitively also. If tag are 3 bits, then it means what? See, if these are the tag are the 2 bits, which means what? That, here you can either hold 0 0 0 1 1 0 1 1, right? Which means if tag are the 2 bits, then 4 of the block from the main memory can map here, right? I mean, the possibilities are 4, and these 2 bits will tell you that exactly which 4 is this, right? So which means it is 4 times bigger, isn't it? The main memory must be the 4 times bigger, then only the 4 is mapping here. Okay, 4 is mapping only to 1. So this tag bits is actually also tell you that how much it is bigger, how much the main memory is bigger than the cache. Okay. So anyway, this particular thing is little advanced, so you will get to understand this more, okay, as we proceed. But yeah, this particular thing is little advanced. That this line whatever I have written here, okay, this particular line might be little advanced. That how the tag size, okay, or the tag bits are determining this main memory size. The ratio between these main memory and the cache size will be 2 power number of bits in tag bits. Okay, this is the ratio, because tag bit says that, okay, if this is 2 bits, then okay, which means 4 of the blocks can map to just one line, which means main memory should be 4 times bigger than the cache. Okay. Okay, great. So some of you have understood, some of you have not understood probably, but yeah, I will just say that, okay, you will get to understand this as we proceed. Okay, so some of you are saying that understood, some of you are saying okay, I mean, only you are saying understood, but some of you are not speaking, but I assume that maybe you have not understood, which is fine. See, if I am writing 0 1 here, then let's just have the whole physical address. Okay, this is the whole physical address. Tag is 0 1. Okay, I don't care about this, block offset. Okay, line number is also given to me. Interestingly, what is the line number for this? This is 0 0, right? Line number is also given to me. Can you not tell me the block number? This is a block number, right? So currently I am holding 0 1 0 0. What is this? This is 4, right? Currently I am holding block number 4. So which means 0 1 2 3 3 4. Okay, this currently I am holding this 4 if the tag is 0 1. Okay, so these kind of questions can easily be asked. Okay, these kind of questions can easily be asked. Let me just ask you, okay, if tag is let's suppose currently, okay, the current tag, let me just ask you, current tag bits are, let's suppose, 0 1 0. Okay, current tag bits are 0 1 0, and number of lines are, let's suppose, 2 power 5. That's going to, okay, this is little big, 2 power 3. Okay, I mean 8 lines are there, or maybe let me write 8 lines. 8 lines are there. Okay, now let me just say that current tag bits of line number 6 is, okay, current tag bits of line number 6 is 0 1 0. A number of lines are 8. Can you tell me that line number 6 is holding which block? From here, can you tell me that line number 6 is holding which block currently? Tell me. I mean, you can just tell me in the binary. Okay, tell me block number in binary. Tell me the block number in binary. See, see. Let me just solve this question. Okay. See what is happening here. Number of lines are 8, right? Which means there are like 3 bits are reserved for the line. Okay, 3 bits are reserved for the line. Okay, 3 bits here. 3 bits are line for the line. This is a block offset. Let's not worry about it. Okay, even if they give some information, let's not worry about it. Okay. Now the tag is also given to us, which is 0 1 0. Okay, tag is 0 1 0. Line number is also given to us, which is 6. 6 means these are the 3 bits which are reserved for the line, right? So 6 means, let's suppose, okay, 6 is 4 plus 2, which is 1 1 0, right? 6 is this, so 1 1 0. So you will say 1 0. I mean, this is the tag, this is the line number. So the block number is 0 1 0 1 1 0. Is this understood to everyone or not? Okay. So I think most of you have guys. Okay, most of you guys have given the correct answer only. Okay, most of you have given the correct answer only. Now let me just modify this question a little bit. I mean, the same question only, just a very small modification. I'm just asking you. See, let's suppose line number 2. Okay, let's suppose line number is 2. Line number 2 means I'm saying 1 0, right? Now tell me, what should be the answer? So let me give you the options. Okay, the one option A is that 0 1 0 0 1 0. Option B is that 0 1 0 1 0. Option C is that 0 1 0 1 0 0. Option D is that 0. Oh, okay, or maybe none of the above. Okay, none of the above. Tell me which option. See here, the tag bits are given to you 0 1 0, right? Since line number, okay, line number is just 2, it doesn't mean you will just write 1 0. Okay, it doesn't mean you will just write 1 0. It will anyway take the 3 bits because number of lines are 8. That's the catch here. It will anyway take the 3 bits. Okay, you cannot write just 1 0. Okay, you cannot say 0 1 0 1 0 is the answer. You have to write as a 3 bits. Line number will anyway take the 3 bits, which is 0 1 0 only. So hence this is the block number. Hence A is the answer. Is this understood to everyone or not? Okay, so as a silly mistake, you might end up doing B as answer. Okay, so B is a silly mistake. Option B could be the silly mistake. You can directly say, okay, 1 0 is the line number, so that's why I should say option B. Okay, option B could be silly mistake. That's why I'm just warning you. Okay, so let's move further. Okay, is this understood? Is this understood? Now let's move further. Now what they're saying, someone is asking if number of lines is not given, then A. No, number of lines they have to give actually. Okay, number of lines they anyway have to give, right? It can't happen. They cannot give. Okay, so maybe can you solve these easy questions? Actually, this is easy question, so maybe I can just little bit move further. Okay, these are the easy questions only, so maybe I can just little bit go further. Okay, so basically let me just solve one two of these questions because these question has been asked in gate, and then I will go to the set associative. Okay, so what they are saying, consider a machine with byte addressable, and then this is 2 power 32 bytes, which means it is 32 bit of the address line. Okay, address is of 32 bit, right? uh, Divided into blocks of the size 32 bytes, so which means 2 power 5, so 5 is the block offset, it is 5, right? Assume the direct map cache having 512 cache lines. Okay, so number of lines are also given 512, which is 9. This is line number is used with the machine. The size of the tag field, can you tell me what is the size of the tag field? Can you tell me quickly? 32 minus 14. Okay, 32 minus 12 is 20, so it will be 18, right? This easy question, I think you understood, right? So 18 bits are required for the tags. Okay, yes, great. So most of you have given the correct answer only, right? 18 bits, right? Most of you have given the correct answer. Let me just quickly paste that answer. Okay, yes, so some of you have given the total address split, that is fine. Okay, now let's just move to this question. I think this question is also easy. So what they are saying, consider a computer system and assume direct map cache. Okay, I think you can solve this question, right? This question is also easy. Okay, just like that you can solve. Block size is given. Okay, probably you can solve, right? Or maybe should I solve this question? Do you want me to solve or you can solve? Okay, so now let's just move to the set associative. So there is a different types. One is called direct mapped, which we have seen. Now the second type is set associative. Okay, okay, let's just move to the second type of the cache, which is a set associative cache. So as I told you that you can put this directly in, exactly you will say that okay, this is the line number which is fixed. I mean, given the block number, can you tell me how to calculate the line number? Divide by, I mean, mod by number of lines, right? Number of lines, that is there in the direct map, right? Set associative says that okay, I will be I can either put in this line or this line. So basically I can put in any of the set. So I will be dividing in the set and then I can put in any of the set. So very intuitively you can understand like this. If these are the 4 sets, so I will be using the same formula only. Okay, I will just say that okay, number of sets. Okay, 4 on number of sets here. Instead of number of lines, I will just say number of sets. Is this little bit okay to everyone? Okay. Okay. So Manish is asking any tips for the AIMT. There is no tip. Just I will just say that just read the question. Okay, properly. Read the question properly. Probably you already might be knowing the answer. Is my video stuck or everything is fine? Okay. So most probably everything should be fine, right? So probably you might already be knowing the answer. It is just that you just have to pay little bit attention or little bit patience is needed. Okay, little bit patience is needed. Question will not be lengthy. Question will be short only in terms of the text. Text length will not be much. For most of the questions, text length will not be much. It will be shorter length only. You just have to read out the question. Just have to have the patience. Probably the question will be easy. You just have to think through it. You don't have to be in hurry while solving the question. I mean, both are necessary. You have to be calm, but not at the same time. You cannot spend more than 5 minutes or something like that. Okay, so questions will be easy only. You just have to be calm in the exam. Okay. So what we will do in the set associative, a block can be placed anywhere within the set, right? So let's just see this set associative. So I will say that this can be put either here or here. I mean, I will be first dividing in the lines, which is fine. Now I will be dividing in the set also. Okay, I will be dividing the cache in the set, and then I will say I can put this either in this set. Okay, sorry, the set number will be fixed, so I will be putting in the this set only. Okay, let's suppose set number 1. Now in the set number 1, either I can put here or here. So basically this particular line or this particular block will go to just one set. Now in this one set I can put anywhere. Okay, that's not a problem. Whichever is empty, I will putting there. So for example, I will be dividing the cache. Obviously it is already divided into the blocks or the lines. Now further I will be dividing in the sets. Okay, I will be grouping the lines in the sets. I will say it is set 0, this is set 1, like this, right? Okay. Now, given this main memory block, this is main memory block, it will go to just one of the set. Okay, will go to exactly one of the set. Is this fine to everyone? Okay. Now let's just see what does this mean. See, let's suppose this is set number which is 00010, right? So here, by the way, here we will be having set number. Okay, instead of line number, we will be having set number, which means I will be dividing my physical address. Okay, physical address into 3 parts. Okay, so there will not be any difference with respect to the block offset. Just like earlier, I will divide in the block offset. Okay, just like the earlier concept. Here I will just tell you how to divide in the set number. Instead of the block number, we call it set number or the line number. Okay, we call it set number, and this is the tag only. Okay, so how to determine the set number? It is same as the line number. Do you remember how to determine the line number? It is basically the block number divided by mod by number of lines, right? In the exactly same way, I will be determining the set number. How to determine this? I will say the set number is equal to block number mod by number of sets. This is called set associative. I mean, I will just determine, okay, in which set it will be going based on the block number in the exactly same way. Okay, set number will be block number mod number of sets. Is this little bit okay to everyone? Okay, this whole thing is a block number. Basically, this is a block number. Now I will be taking the mod. Mod means taking this remainder part. Okay. Okay, so let's just see this question directly, and then you will get to understand that what I'm trying to say. Okay. No, a set can come. Set can have more than two. For example, these are the four lines. Okay, it will just be given in the question. It is called k-way set associative. If they are saying two-way, it means set size, set size. Okay, or number of lines in the set is k. Number of lines in set is basically, they will tell you like this, k way. Okay, it is k, which is 2. They will say k way set associative. Okay, now they are saying there are 256 sets. Okay, so total there are 256 sets. This is set 0, or maybe it doesn't matter, the numbering doesn't matter, but yeah, there are 256 sets total. Each set contains 2 lines. Okay, this is line 1, line 2. Now how many lines are there? If each set contains 2 lines, 256 are the sets. Each set contains 2 lines, so I think 512 lines, right? So C is the correct answer. Is this okay to everyone? Is this okay to everyone? Okay. Now let's just solve this question. They are saying 4-way set associative cache, 16 byte blocks. Okay, so block size is given to you as 16 bytes, which means if you divide, the block offset will be 4. Okay, this is your block offset. Now a total of 128 blocks. See, if it could have been direct map, see, this is the cache, right? Okay, so if this could have been the direct map, I could have directly said, okay, 7 is the line number. Can I directly say this? See, if these are the number of lines, can you tell me number of blocks? Sorry, number of sets? What are the number of sets? Each set contains 4 lines. Okay, see, each set contains 4 lines, right? If 128 is the total lines, the number of sets will be always number of lines, which is 128 divided by 4, which means 2 power 7 divided by 2 power 2, which is 2 power 5. 2 power 5 is number of sets. This is the most important number that you first have to find out, number of sets. How many number of sets are there? Okay, these are number of sets. Is this fine to everyone? Now you will be writing set number. That's why this is 5. Okay, this is the set number. See, first you have to find out number of sets, then everything is just like the direct map. I mean, instead of set, if you want to read it line, once you find out the number of sets, you can just say set and line is same. Okay, I mean, every mathematics is same, just you have to find out number of sets. Once you find out number of set, everything is same. Okay, just instead of set number, we call it line number. Okay, you just write 5 here. I mean, you can now call line, set, doesn't matter, but the 5 is important. Okay, you have to write the 5 here. Okay, and then this is automatically, if this is 64 bits, okay, 64 is too much, but yeah, that's fine. 64 minus 9 is 64 minus 10 is 54, so it is 55, right? Okay, so 55 will be here, which is a tag bits, right? So what is the byte offset? 4. Or the block offset, byte offset is same. Index is 5. We index in this case is set number. Index in case of the direct map was the line number. What are the tag bits? Tag bits are 55. So 4, 5 and 55 is the answer. Okay, answer is not written here, but 4, 5 and 55 is the answer. Okay, is this okay to everyone? Let me know. Okay, so I think it should be understood, right? Okay, now let's just move to the next question. Okay, 32 KB 4-way set associative. KB means 2 power 10 is K. 32 means 2 power 5, right? These many bytes. 2 power 15 bytes is your cache size, right? And which is set associative, which is fine. Array with the 32 byte line size. Okay, so line size is 2 power 5 bytes. So first tell me immediately number of lines. 2 power 15 divided by 2 power 5, 2 power 10. Number of sets, 2 power 10 divided by 2 power 2, because it is 4-way, it means divided by 4, which is 2 power 8. These are the number of sets. Okay, now you can, the number of sets is 2 power 8. How many? Now you can immediately do this. Okay, they should give the physical memory size. I think they forgot, but let's just assume this to be 32 KB. Okay, let's just assume this to be some number, maybe 24 bits. Okay, suppose this is 24. Okay, now let's just do this question. So line size is 5 is your block offset. This is 8. 8 plus 5, 13. What is remaining here? 11, right? 1185 will be your answer. Is this okay to everyone? Okay. Okay. Now let's just do this question quickly, and then you will get to understand the set associative very clearly. I mean, the set associative part will be ultra clear once you solve this question. Do you want to attempt this question quickly? Let me know. So what they are saying, they have given you some numbers, right? They have given you some numbers, and then they are asking you to calculate the other numbers. I mean, they have given the block size and lines per set, which means the associativity. Okay, they're asking you cache sets. How many sets are there? Okay, so let's just see this. Suppose they are saying that block size is 8. That's fine. Lines per set. So they are saying that this is 4-way set associative. How many lines are there? First, you have to find out how many lines are there. So this is 32-bit address. 2 power 10 is your cache size, right? So let me write the number of lines here. Okay, so this could be the number of lines column. Okay, so I can say number of lines. So if this is 2 power 10, this is 2 power 3, then 2 power 7 is the number of lines. Or yeah, 2 power 7 I can say. This is 2 power 10, 2 power 7. This is 4, so 6. This is 4, so 6. This is 5, so 5. And then 5, right? Is this okay to everyone? Now, how many sets are there? Number of cache sets. If number of lines are this, then 2 power 7 divided by 2 power 2, right? 2 power 7 divided by 2 power 2, which means 2 power 5. Okay, so this is 2 power 5. Again, 2 power 7, this is 2 power 6. So this is 2 power 0, this is 2 power 5, this is 2 power 0, this is 2 power 3. Okay, so this is 2 power 5, this is 2 power 1, this is 2 power 6, this is 2, this is 2 power 5, this is 2 power 2. Okay, 2 power 5, 2, 2 power 6, 2 power 2, 2 power 5, and 2 power 2. Yes, these are correct. Okay. Okay, now what is that next question? Tag bits. Okay, let's just check what is your 32-bit machine. Okay, so you have 32-bit machine, right? You forget about your block offset. What is the block size? This is 3. I mean, you just keep it aside, and then 3 plus this is 5, right? 3 plus 5, 8. Okay, and then what is remaining here from 32? So 32 minus 8, which means 24, right? So 24 will be the number here. Now similarly, you can calculate this. This 2 will come here, right? Your sorry, this is 2 power 1, right? So 1 will come here, and this is the block offset is 3. So this is 4, and then 28, right? 4 plus this. So can you do all of this? So index is very easy. Index, you can just take the log of this. Okay, index is very easy. Block offset is anyway very easy, right? You can take the log of this. These two are very easy. Tag is little calculation. You can do this very easily. Okay, can you do this? I think this is now doable. Okay, great. So the answers on the next page. Okay, let's solve this question. Probably after this you will be very much habitual, and then we will be having the gate questions. Okay, let's solve this question. So what they're saying, cache size is given, which is 2 power 5 into 2 power 10, which is 2 power 15 bytes. Cache size is given like this, and number of lines are also given, which is 2 power 10 is 1024, 2 power 11 is 2048, right? So this is 2 power 11. Okay, so I can say 2 power 11. Okay. So number of lines are there. Can you tell me number of sets? 2 power 9, right? So number of sets are 2 power 9. Line size. Okay. So they are saying cache is 2 power 15 bytes. These many lines are there. So how many, what will the line size? So you can say the cache you will be dividing into two parts. This is 15, right? This is 15. Now these are the lines. So line number is 11 anyway. This is 4. So line size will be 2 power 4 bytes. This was little interesting. Index bits. Tell me the index bits, which will be number of sets, right? So I think 9, right? Offset bits, which is the line, which is 11. So 2 power 4, 2 power 9, 9 and 11. 2 power 4, 2 power 9. Sorry, offset is line size, right? Okay, sorry. I don't know why I've written 11. Offset is anyway 4, right? Is this okay to everyone? Okay. Now let's solve this question. This is little interesting question. What they are saying, the physical address of the processor. This question has been asked in GATE 2018. This was the year when Deepak has appeared. Okay, Deepak has appeared for the GATE, and he has got the top rank. Okay. Now the size of the physical address space of the processor is 2 power p bytes. So which means p bit address, right? P bit address. If 2 power p is the size of the address space, then 2 power then p bits are the length of the address, right? P bit address. Okay. The word length. So basically, they're talking in the word. So what you can do, you can divide. I mean, you can have everything in the word because they are asking in the words. Okay. So you can say if 2 power p bytes, then 2 power p minus w, or 2 power p. You can say 2 power p bytes is your address space size, or in the words it will be 2 power p minus w, right? This will be your address space size. Is this okay to everyone? That what I'm trying to say? So basically it will be you can just divide by the word length, and then you will be getting 2 power p minus w. Okay. So you can say p minus w is your address, number of bits in terms of the word. Let me know if that is okay to everyone, or there is any confusion here. Okay. Okay. Now what they are saying next, the capacity of the cache memory is 2 power 9 2 power n bytes. So they are saying, let me just remove this. Cache memory is 2 power n, that is fine. The size of the cache block is m by words. So cache block size is m words. So basically m 2 power m, which means m you will be keeping here, right? Now this will be your index. This is k-way set associative anyway. So this is your index, or you can say set number. Okay. This is your tag. What they're asking is tag bits. Okay, they're asking for the tag bits, right? The length of the tag bits. So do you want to solve this question? You actually have to find out the index, right? Index means number of sets. You just need to know what are the number of sets. Okay. For that, first tell me what are the number of lines. Okay. What are the number of lines? What is the formula of number of lines? What is the cache size? 2 power n bytes in terms of the word. So first convert in terms of the word. This is the cache size, right? So this will be your cache size. Divided by line size. What is your line size? Cache block is 2 power m bars, right? 2 power m. So your number of lines will be 2 power n minus w minus m. Is this okay? N minus w minus m. Now your number of sets will be how much? Okay. Given this, can you tell me number of sets? Okay, that's easy only. They are just having some confusion just because they have given an n w or like this. Now tell me number of sets. Just go step by step. Okay, number of sets. What are the number of sets? Number of lines n minus w minus m. Number of lines divided by the associativity, which is k. It will be divided by 2 power k or it will be divided by k. Tell me. It will be divided by k or it will be divided by 2 power k. It will be divided by k, right? It will be divided by k, not 2 power k, because it will be associative, which is k. You can actually rewrite this k as in the terms of 2 power. Can you write this log base 2k? I mean, generally this get cancelled out, so it is basically same as saying 2 power n minus w minus m divided by 2 power log base 2k, right? I mean, I'm just rewriting this k in the 2 power so that I can just have the easier calculation. So it will be n minus w minus m minus log base 2k. Is this okay to everyone? These are the number of sets. If these are the number of sets, then immediately you tell me what is the index bits n minus w minus m minus log base 2k. What are the tag bits then? P minus w minus this whole thing. I mean, you can just add these two. So I think m will get cancelled out. To p minus w. So minus w and minus w got p minus n plus log k. So p minus n plus log k. So what is the answer? B is the answer. Okay. P minus n plus log k. Is this okay to you guys or not? Let me know. Okay. So I hope that is fine, right? Okay. Okay, I should repeat. See, let me just tell you here. You first convert everything into the words, okay? Then this is given to you. They are saying this is word size. I mean the block size is given to you. This p minus w is also given to you. You just have to find out number of sets. For that you find out number of lines, which is cache size divided by line size, right? So what is the line size? 2 power m, right? So you divide by like this. It is number of lines. For the number of set, you again divide by k, and then you will be getting number of sets. The only trick here is to find out the number of sets. Once you find out the number of sets, everything will be set. Okay, everything will be easy. Once you find out in the set associative, you find out the number of sets only. Okay, which is once you find out the number of lines, number of sets will be easy. So it is number of lines divided by set associative. How to find out the number of lines? It is whatever is your cache size divided by line size. Okay, cache size divided by line size. That's how you find out number of lines. Is this okay to everyone? Okay. Now let's solve this question. Okay. So what they're saying is the cache memory initially uses 6 bits for the tag in a two-way set associative design. How many bits will it be needed for the tags when changing it to 4-way? So they are saying that initially it needed 6 bits for the two-way associative. Okay, so it was two-way associative and it needed 6 bits for the tags. So here you have 6 bits and it is two-way set associative. Now if you are going to be the 4-way, okay, and if everything is same, then the block offset won't change, right? So from 2-way to 4-way, you just tell me number of sets will decrease or increase. See, if you are grouping into just two lines, okay, two lines, two lines, right? There is another possibility, you are grouping into four lines, okay, four lines like this. So number of sets will be decrease or increase here? Number of sets will be more here, right? Number of sets will be decreasing. So if it is four way, then number of sets will be how much? You can say divide by 2. Whatever earlier number of sets were there, if number of sets are x here, then x by 2 number of sets will be here. Is this okay to everyone? Number of sets will actually decrease. So this is representing index. This is representing number of sets, right? So earlier, if it is, let's suppose instead of x, let me take 2 power x, okay? I mean, the calculation will be easy. Earlier, if 2 power x is number of sets or x is the number of bits in the index, 2 way, and in the 4 way, then it will be 2 power x divided by 2. Then x minus 1. Isn't this will the index? Now, the block offset will remain same. Whatever is the index bits, it will actually decrease by 1, not by 2 or multiply, not like this, right? Number of index bits will decrease by 1. This is very important observation. See, if the number of sets are decreasing, then it means number of sets will get divided by 2. Whenever you are dividing something by 2, then instead of assuming x, since it is a variable, so instead of assuming x, you assume 2 power x. 2 power x is number of sets here. Then what is the number of sets here? 2 power x divided by 2. Okay, if 2 power x is number of sets here, okay, I'm assuming 2 power x. You can assume x, but the calculation will be little, trickier or tougher. So I'm assuming number of sets are 2 power x. Then here number of sets are 2 power x minus 1. So if x is the number of, tag bits, the index bits, then index bit is x minus 1 here. Is this understood to you guys or not? Then whatever is the tag bits, since the whole thing is same, right? I mean, if you are, see, this is just a bar, okay? If you are just shifting this bar here, I mean, if you are compressing it, I mean, if you are taking you are putting this here, then this, if this is y, then this will be y plus 1. I mean, this will increase. So it is just like a bar, okay? Just like a bar. If you are pushing it here, you are decreasing this index, x minus 1, then automatically this will increase, right? So what they are saying, if earlier this is 6, then this will be how much? You are actually shifting it like little bit. This will be how much? This is x minus 1. Or I mean, you are decreasing this by 1, then this will be increased by 1. So it will be how much? Can you tell me? It will be 7, right? Is this understood to you guys or not? Let me know. I hope it is understood, right? Okay. So now let me ask you another question. Suppose earlier, it is 4-way set associative and number of index bits are 3. Now let's suppose I'm making some change and it is now, let's suppose, 2-way set associative. Okay. Now you tell me number of index bits will be how much? See, from 4-way, you are going 2-way, right? You are going 2-way. So, number of sets, earlier if it is, let's suppose, two sets, then it will be 1, 2, 3, 4, right? So it will be double. Number of sets will be double, right? So you can say number of sets will be doubled. So whatever is the here, so earlier if this is 3, so number of sets is 2 power 3. Now the number of sets will be 2 power 3 into 2. So it will be 4, right? It will be 4. So number of index bits will be 4. Is this okay to you guys? Let me ask you the next question. Suppose earlier your setup is something like this. Okay, your setup is this is 3, this is 2, this is 4. Okay, and let's suppose this is 8-way set associative. Now quickly tell me, now if I do 2-way, tell me the address is split quickly. Okay, tell me the address is split quickly. If I do 2-way, now it is 2-way. From 8-way, which means 8 to 2, then number of sets will be thrice. I mean, sorry, if it is 8 and I'm going to 2-way, right? So how much? 2 power 3, 2 power 1, 2 power 2. Okay, 4 times. So basically 4 times. Yeah, number of sets will be 4 times basically, right? So this is 2, since it will be 4 times, so 2 power 2. So basically it will be 4, right? I mean, plus 2 will be there. If it is plus 2, then it will be anyway 2, because this is constant, because this 3 is anyway there, right? So 2, 4, 3 should be the answer. Is this understood? Is this understood to you guys? Okay, right? Now, I hope you understood this. Now let's just answer this question. A computer system has a computer system has 4 keyword cache organized in block set associative manner with 4 blocks per set. Okay, so 4-way as a 4K word. Okay, this is just one. This is 4K. I thought. Okay, so the cache size is given to us 2 power 2 into 2 power 10 words, which is 2 power 12 words, right? 4 blocks per set. Okay, so 4 blocks per set means that 4-way set associative. 64 words per block. So block size is given to you as 64 words, which means 2 power 6, which means this is 6, right? Block offset. Number of bits in the set and word field. Okay, so you need to find this set. Word is anyway 6. So okay, so only one of the option is matching. So actually word is anyways, word means block offset, or byte offset or word offset is same. So anyway, like only D is matching this. I mean, you anyway don't need to find out, but for the completion, let's just do it. Okay, so they are asking the index words. So can you tell me how many sets will be there? Cache size is given to you. Line size is also given, right? So you need to find out number of lines. Cache size divided by line size. What is the line size? 2 power 6, right? 2 power 6, and then divide by this 4, which is 2 power 4. So 4 will be here, right? So it's easy question, I think. Okay. Okay. Now let's just move to the next question. So what they are saying, I think these questions you can do probably, right? Yeah. Let's do this question. This is a bit interesting question. After these 2-3 questions, I think. Yeah. Let's do these interesting questions. Okay. And then we will move to the full associative cache. Okay. So they're saying the main memory has main memory of a computer has 2 cm blocks. Okay, so number of blocks are given to you. Number of blocks in main memory. It is in main memory, remember, okay? 2 cm. Cache has 2C blocks. Okay, number of blocks or lines, let me write blocks only, in cache is 2C. Okay, by the way, from this, can you tell me tag bits? It's interesting. I'm just asking you, if even if you don't tell me, that's fine. From this, can you tell me the tag bits? Yes, Shivam, you can use formula, but that's fine if you just do it from the scratch. So yeah, actually tag bits are the ratio. Okay, so tag bits are actually m, but that's fine. Okay, so tag bits are the ratio of main memory and the cache size. If the cache uses set associative mapping with two blocks per set, so associative, let me write it as k, is 2 is given to you. Okay, or maybe let me write two-way set associative. Two-way set associative. Then block k of main memory maps to which set? Okay, so let's just solve this question. See, block k of main memory. See, block k will map to which line? Can you first tell me? Okay, they are directly asking the set. Okay, can you tell me block k will map to which set? It will depend on number of sets only, right? So if this is the block number, then you can just divide by the number of sets. So how many sets you have? First, let's just find out number of sets. So if it is, I don't think it was anyway needed. Okay, so number of blocks you have, and it's two way. So can you find out the number of sets? Okay, so 2C is the lines and 2 year grouping, right? So I think number of sets will be C. Is this okay to everyone? Number of sets will be C, right? That's very easy. Now, do you know how to map block number to the set number? If block number k is given to you, they're just asking you the set number. You know the mapping formula? It is just mod by the number of sets, which is C. So k mod C, right? K mod C should be the answer. So B is the correct answer. I mean that this information is not at all needed for this question, but that's fine. Yeah, B is the correct answer. K mod C, right? Okay. C is the number of sets. Okay, and then K mod C. That's easy question only. Isn't it very easy? You just need to know this. Okay, the block and set number are how they are related. Generally people actually don't know these things, so that's why they do mistakes in the decimal. I mean this is not exactly decimal, they have given in the decimal format, in the sense that I mean they have not given the numbers, but yeah, these are the k, I mean the notations are anyway in the decimal, right? So in decimal people actually get confused, but you just remember the basic principle that okay, block number and set number are related by the mod operation, right? Is this okay to everyone? So yes, I will put the link of this, lecture notes here in the comments. So don't worry about the link of the notes. Okay, I will putting. Okay, okay. Now let's just move to the next question. So this question is again easy one. So let me just skip these questions because these are the easy questions. Let's do this question. This is little interesting one. Okay, let's do this question. I mean this question should be doable, but still let's just do this. So what they are saying, that a cache memory is having the capacity of n words and the block size of b words. Okay, is designed to be, if it is a direct map cache, the length of the tag field. So they are saying earlier it is tag bits are 10 and it is direct mapped. Okay, direct mapped. Now they are saying it is set associative. Now it is 16-way set associative, right? In the length of the tag field. Now the tag has become what? So see, earlier this is 10. Okay. Let's suppose you don't know number of lines. Okay, number of lines could be anything. Number of lines could be anything. Now the block size will be anyway same here. Now tell me this index bits. It will be obviously decreased or increased. Tell me this particular thing. If you're dividing into the sets, then obviously it will be, so basically the index bits will be less, right? It will be decreased because number of lines will be anyway more. So it will be anyway more. So it will be decreased by -4. So it will be -4, right? Which means you're shifting this bar here. You're shifting this bar 4. So it will be, this bar will be increased by +4. So it is 10 + 4, right? Is this understood to you guys or not? Let me know. This will be 10 + 4. So what is the answer? 14 should be the correct answer here. Okay. So you are basically shifting the bar. So once you understand that how you are shifting and everything is happening, you can solve this question easily, right? Yes, that is an interesting question, isn't it? How many of you found this question interesting? Okay, great. Now let's solve this question. This question is actually nice question. I can say it is, little nice in the sense that it could be not directly easy. It is little. I mean, it is easy only, but it's not too tough. Okay, it's not too tough. It is, I can say, medium. Let's say what they are saying. Just like that question only. It is just like that question. See, in this question, I think this is 1999 question. Here they are saying that block number is given. They are asking the set number. Okay. Now here they have given the block number. Let me just tell you. Block number J. They are saying that okay, this is the block number. Now they are saying, see, we know the set number, how to find out the set number, right? How to find out the set number? We can do this using the mod operation, using the number of sets. Okay. So suppose these are the V sets. It is also given the B sets. I will read out the question, but before that, I'm just telling you a glimpse of the question. So the set number, J mod B, right? J mod B. I mean, this is the GATE 1999 question. Okay, so in GATE 99 they just asked this, but here they have just little bit asking advanced. They are saying, okay, set number is okay. Give me the line number also. They are saying, give me the line number. I mean, you cannot directly give the line number. It will be in one of the line. So they're saying, tell me, given the set number, tell me it will be within, which line. Okay, something like this. Let me just read out this question. But yeah, they are asking about the line number. This is the outline of this question. Okay. Okay, so someone is asking, sir, set associative में cache line bits और number of sets का relation क्या होगा? Cache line bits, number of sets. I'm not getting your question. Okay, so let me just continue with this. Now what they are saying, it is k-based set associative. Okay, which means each set is having the k lines. The cache is divided into v sets. Each of this consists of k lines. That's fine. I mean, that is already written. The line of the sets are placed in the sequence of one another. The lines in the sets are in the set S are sequenced before line S plus 1. I mean, that's a usual setting. The memory blocks are numbered from. Okay. So I think only one more information which is needed is k-way set associative. Okay. So basically they are saying, tell me the line number, the possible line numbers it can map to if it is k-way set associative. Okay. This is the only question. So let me just answer this question. See, given the set number, let's suppose it is k-way set associative. Okay. Let's suppose it is 4-way set associative. Okay. Then it contains, the first set contains 0, 1, 2, 3, right? The second set contains, okay, I mean, whenever I say set number, you cannot say, okay, just a second, what I'm saying. So see, if it is 4-way set associative, so first set will be containing 0, 1, 2, 3, then it will be containing 4, 5, 6, 7, like this, right? Okay. So can you tell me set number 0? Set number 0 is having the line from 0 to 3. Set number 1 is having the lines from 4 to 7. This is set number 1. Right? Like this. Set number 2 is having lines from 8 to 11. Something like this. right? So given any set number, let's suppose x, can you tell me for the set number x, what are the possible lines? Set number x will range from which line to which line? Set number x. See here, set number 0, 0 to 3, set number 1, 4 to 7, which means see, it will be containing 4, right? And then 4. So basically 4x, right? If you notice, it will be 4 into this, 4 into this, 4 into this, 4x to 4x plus 3, I think, right? Okay. So set number x will be having these lines. If this is understood, then this question is direct. Let me know if that is okay. Okay, 4x to 4x plus 3. Great, great. I'm really glad to see that most of you have given the correct answer. 4x to 4x plus 3. Once you answer this, then everything is very straightforward, right? Now you tell me, if you know this, then can you tell me that set number j mod v, okay, if the set number is j mod b, okay, associative is k, then can you tell me the line numbers will be j mod b into k, right? Into k, 2, I mean the same thing, plus k minus 1 basically, right? 2 j mod v into k plus k minus 1. Okay, so j mod v into k, 2 j mod v into k plus k minus 1. Yes, so a is the correct answer. Okay, so let me just revise this question. What they are saying, block number is given to you, it is k, sorry, let me just check, it is j. Okay, block number is j, block number is given to you as j. Okay, now next thing they are saying, given this block number, okay, don't just tell me the set number. I mean, this is the intermediate step that you anyway have to do. Tell me also the possible 9 numbers that the set has. Okay, just one more step they have added. If this is j, and if this is, okay, block number and set, if this is number of sets are let's suppose v. Okay, so number of sets are v, then set number will be j mod v. Okay, this will be your set number. Is this understood to everyone? And what are the line numbers? See, for any set number x, and if it is 4-way set associative, then 4x to 4x plus 3. If it is k-way set associative, so it is k into j mod v into k to j mod v into k plus k minus 1. Okay, these are the possible lines that you have in this set. Okay, so they are just having one extra step here. Okay, the similar question has been asked in gate, but they are having one extra step here. That is all. Is this okay to you guys? Okay. Now let's just solve this question. This is quite tricky or interesting question actually. So by the way, in this question, there seems to be little, okay, not much, seems to be little mistake in this question. Instead of a greater than equal to k, it is actually a greater k. Okay, so let me just read out this question. But there seems to be, gate has done little mistake. It is actually a greater than k, but that's fine. Okay, so what they are saying, let me just tell you what they are saying. They are saying that in excess of, they are actually accessing some blocks, okay, and addresses of length n. So they actually have total access. Okay, so they are saying total number of access they are making. Total number of access is n, capital N. This is the total number of access they are making, and then they are making n unique access. So what does this mean? So let me first walk you through the questions, and then I will just solve this question. So they are saying that suppose let me just write it. You are accessing some blocks. Let's suppose this is block number 5, then you are accessing block number 3, then you are accessing block number 10, then you are again accessing block number 3. Okay, it can happen, right? Then you are accessing block number 10, then you are accessing block number 5, then you are again accessing block number 10, then you are again accessing block number 3. So tell me how many total access you are doing. 1 2 3 4 5 6 7 8. So they are saying total you are accessing 8 blocks. Okay, now you might be repeating some access. For example, you are accessing this 5, and then you're again accessing this 5. Similarly, you're accessing 10, again accessing. So your repetition might be there. Now you tell me here in this particular case, okay, you tell me what are your unique number of blocks you are accessing. Either you are accessing 3, you are accessing 5, or you are accessing 10. So they are saying unique access is represented by small n. In this case it is 3, right? Is this fine to everyone? This is 8. Okay, this is 8. Okay, this is 3. Is this fine? Now they are saying small n is the unique access, capital N is the total access. The number of unique block access. Okay, now they are again saying that in between two axes of the same block, okay, in consecutive access to the same block address, it is bounded by k. Okay, which means they are saying, let's suppose k is 4, which means it can never go beyond 4. Okay, let's suppose k is 4. Okay, so which means they are saying if you are accessing this 5 again, then number of blocks in between that you are accessing, okay, it is at most 4. Okay, at most in between you will be accessing 4. At most 4 you will be accessing. See, here in between you are accessing 1. Okay, they are saying number of unique blocks addresses between two consecutive addresses of the same block is bounded. Okay, unique block anyway you are doing 1 2. Okay, unique block anyway you are doing 2, but yeah, let's suppose k is 4. Okay, k is 4 means at most you can access 4 different. Here in between these two, at most 4 different could be there. Okay, 4 unique could be there. In this case it is 2, but yeah, at most 4 unique could be there, let's suppose. Okay, now what they are saying, what is the ratio if we access the sequence passed through the cache associative A? Okay, see, they are asking about the miss ratio. Okay, they are asking about the miss ratio. What is the miss ratio? This question is little tricky, but let's just try to understand this question, okay, carefully. So they are saying, see, if you are accessing an unique access, then in that case, can you say, if you are accessing n blocks uniquely, in that case, can you say that there will be at least n miss will be there out of small n, out of capital N? So at least miss ratio will be there, at least. Okay, this is the at least miss ratio. At least these many miss you will be doing. If these are the unique, I mean, first time whenever you do, it will be miss, right? First time whenever you are accessing 5, it will be miss. So at least n misses will be there, small n, out of capital N. Now if set, this is a set, okay, this is a completely one set. If set associative T is A, let's suppose A is 5, which means 1 2 3 4 5. Okay, so suppose in a set there are 5 lines. This is capital A. These are the 5 lines, okay, that you can hold. Now suppose in worst case everything is actually mapping to, let's suppose, only this set. Okay, so this 5 will come here. Now before you access next 5, okay, how many at most can come? 4, right? How many at most can come? 4. So basically these 4 can accommodate here. I mean, what I'm trying to say, whenever this next 5 is coming, it will be hit only. It will not be miss. It will be hit only. So you will be missing, okay, you will be missing only on the first 5. I mean, there will, in the second iteration, it will be hit only. So here it will be hit only. So that is the key point here. Okay, it will be hit. Now it is a repetition. So in the sense, whenever there is a next 5, it will be hit only, because in between there could be at most 4 only. Okay. And there is something called least recently used. So basically you will not be replacing 5, you will be replacing something else. So whenever 5 is coming, it will always be there. Okay. So that's why whenever next time it is coming, it is hit only. See, small n at least will be there, but it could be plus something, right? Plus something extra misses. Okay, which means maybe I miss the next 5 also. See, this is a compulsory miss. I have to anyway miss on this. Okay, this is a compulsory miss. I mean, whenever you are accessing first time, it is a compulsory miss. Okay, it is compulsory. But whenever you are accessing next time, it may be hit or miss. Okay, that's why I'm saying it may be something plus something. But we observe that it will be hit only. Why? Because at most 4 unique can come and 4 can accommodate here. Right? So that is why next time also it is a hit. Hence, it will be small n by capital N. It is a little tricky question. I don't want to go in much detail. But yeah, if you want to solve, I have given the hint. So small n by capital N is the answer here. So A is the correct answer for this particular question. Okay. Okay, so don't worry if you have not understood this question. It is little tricky because of the wording and all. But all they are trying to say that whenever you are next time accessing this, the number of unique blocks which will be coming will not be more than 4. Okay, so anyway they will accommodate here, right? So 5 will anyway there, right? I mean it will be hit on the 5. Okay. Okay. So I think we have covered, many of the things here. Now we will be having one more session. Actually, I wanted to cover till loop complexity. I mean the miss rates and all in the loops. Okay, I wanted to cover these kind of questions also, but probably there is a less time today because I wanted to cover this. So we will be having one more session for the cache memory itself. Okay, where we will be covering these kind of questions, and I will be taking this session soon in just 2-3 days, and where I will be covering these kind of questions also. Okay. So today let's just wrap this up. Okay, because the session will otherwise go too long. Let's just wrap up this session. So let me just tell you that what we have been doing. We have solved almost all kind of these questions. Now these questions are still remaining. These are interesting and easy questions only. Okay, these are the easy questions only. These are still remaining. In AIMT, we will definitely ask questions from the cache memory. We will definitely be asking questions from this part also. Okay. So by the way, about the AIMT, you can attempt it on the Sunday, which is 22nd of December at 2:30 p.m. Okay. So that is all I wanted to discuss. If there is anything, you can just let me know. I just request you one thing, that what you can do, you can just comment out. Okay, if you have understood everything, just comment out under the session. Okay, just let me know. Just comment after the session end. It will motivate us a lot. Okay, just say just one word. Okay, just one word. Maybe if you have liked the session, just say loved it. Okay, just one word. Okay, whenever you are watching it, okay, you are watching it later or you are watching it now, whenever you are watching it, just comment it out in the comment section, so that YouTube recommend it, and we also got motivated, right? Whenever we see the comments and all, we also got motivated. So just comment it out and let us know that how you like this session. Okay. How many marathons? It's not a fixed number. There will be, depending on the time and everything. So generally most of the topics I can say are already covered in the marathon session. So you can search like Go Classes marathon, and then you will be getting all the marathons. So we have covered last year, many topics we have covered last year, many topics we will be covering this year. Okay, so it's not a fixed number. I mean there will be many topics this year also. There was many topics last year that we have covered. There will be many topics this year also. So it's not a fixed number. We will be just depending on the time, we will keep on taking the sessions now. Okay, because it is a high time to take the marathon sessions. Okay, thank you everyone. Take care. Bye bye.